Welcome back to Integration by Substitution, Part 2. Let's talk about how we can use integration by substitution to evaluate definite integrals. So let's look at the definite integral from -1 to 1 of x squared plus 4x cubed minus 11 quantity cubed dx. All right, so what we're going to do is we're going to let u be 4x cubed minus 11, and then we'll let du be 12x squared dx. Now, if we do that, as you can see, that here's the x squared dx, we're missing the 12. So let's just focus on the indefinite integral for just a moment. So let's ignore the bounds from -1 to 1. So here we have our x squared 4x cubed minus 11x quantity cubed dx, and I need that 12, so we know to put a 12 here, and we'll have to counteract that with a 1 over 12. So now we've got u being raised to the third power, and this 12x squared dx will make our du. So we have 1 over 12 u cubed du. That's something we can integrate, right? That's going to be 1 over 12 u to the 3 plus 1 over 3 plus 1 plus c. And so that ends up giving us 1 over 48, 4x cubed minus 11 to the fourth power plus c. So that's for the indefinite integral. Now, with the definite integral, we don't have a constant of integration. We're actually evaluating it at our bounds, right? We're going to use that fundamental theorem of calculus. This right here without the c is my big F, and we'll do f of b minus f of a here. And so we'll evaluate, instead of this plus c, we'll evaluate it from -1 to 1. So we'll take 1 over 48 times 4 times 1 cubed minus 11 to the fourth, minus 1 over 48 times 4 times -1 to the third minus 11. This is my f of b minus f of a. And when I do that, I get -3014 thirds. But there's a little bit of a different way. There's another way we can do that that might be a little bit quicker and maybe even a little bit easier. Instead, when we do our u substitution like we did before, just like we did, and instead of calling it an indefinite integral, we can change the bounds from -1 to 1. We can change them into u and take whatever we had u to be and evaluate it at the lower bound, evaluate it at the upper bound, and we change the bounds. So now we'll evaluate that 1 over u to the fourth at u at 1, which is 4 times 1 cubed minus 11, and u at -1, which is 4 times -1 cubed minus 11, which means we're going to evaluate this 1 over 48 u to the fourth from -15 to -7. And when I do that, I end up with that same answer, -3014 thirds. So instead of having to integrate in terms of x, use u substitution, go back into x to do your plug-in with your bounds, we can actually just change the bounds in terms of u. Let's see another example of that. Let's take the definite integral of dx over x natural log of x from e to e cubed. All right, so we need to pick something to be our u. We'll pick u to be the natural log of x, and then du would be 1 over x dx. So now we have this 1 over x dx right here, which will be replaced with du, and this natural log of x, which will be replaced with u. And then, so we can rewrite this, right? If you need to see it out, dx over x natural log of x is 1 over the natural log of x times 1 over x dx. And so now I can do my 1 over u times du, but instead of doing the indefinite integral and then doing it in terms of u and plugging back in for x, I will change my bounds. I'll change my upper bounds to be u evaluated at my original upper bound, e cubed, and I'll take my lower bound and do u evaluated at my original lower bound, e. And when I do that, u evaluated at e cubed is going to be 3. Right? Natural log of e cubed, which is going to be 3. And then the lower bound will be the natural log of e, which is going to be 1. And the antiderivative of 1 over u du is the natural log of u. So now I have the natural log of u evaluated from 1 to 3, which will give me the natural log of 3 minus the natural log of 1, which is the natural log of 3 minus 0, which is the natural log of 3. Now, I realize that back here you're probably asking, why didn't I put absolute value signs here? Because my bounds are positive, So I know that I'm plugging in these positive bounds, so it wasn't necessary. But when you're talking about like the indefinite integral, or if you were plugging in bounds that could potentially be negative, then that absolute value will be important there. Let's do another one. The definite integral from 1 to 2 of x times the square root of x minus 1. All right, so we know what we want to do is try to pick u to be what's underneath the radical, so we'll let u be x minus 1. So then du is going to be 1 dx. That leaves us with this extra x right here. Well, like we talked about last time, since we know that u is x minus 1, that means that x is u plus 1. So we can substitute that in. We can replace this x with u plus 1. We can replace this x minus 1 under here with u. And we'll change our bounds to be u evaluated at the upper bound and u evaluated at the lower bound. This is really u to the 1/2. So then I'll distribute that u. U at 2 would be 2 minus 1. U at 1 would be 1 minus 1. So what I have here is the bounds from 0 to 1 of u to the 3/2 plus u to the 1/2 du. Now I can evaluate that definite integral. That's going to be u to the 5/2 divided by 5/2 plus u to the 3/2 divided by 3/2. And instead of dividing by fractions, we multiply by their reciprocals. And instead of a plus c, we're going to evaluate this from 0 to 1. So we'll plug 1 in, plug 0 in, and subtract those two values. This right here is going to give me 2/5 plus 2/3. This is going to give me 0, and I'm left with 16/15. And so that's how you do definite integration by substitution. So review these videos, and I'll see you next time.